Okay. So tell me now, are you able to see the screen now? No?
Yes, sir.
MATLAB, okay. Yeah. So now in the second transfer function, that is for the power system block, kps by 1 plus stps, kps value equal to 100 on the numerator, whereas the denominator we have stps, 1 plus stps, 1 plus s coefficient is the tps value equal to 20. So that's why we are keeping here as a 20s plus 1, 20s plus 1. So 100 divided by 1 plus 20s or 20s plus 1, right? Now, actually, our main motto is I want to observe what is the frequency deviation, how frequency is deviated with respect to the time when there is a change in demand by a value of 0.01 per unit. Value 0.01 per unit. So if you want to see that one, if you want to see that output, see the frequency response, so you have to take the one more block from the sinks. From the sinks, you are able to see the scope block. So take this scope block onto the project. So just connect. So in the scope block is used to observe the output, to see the output, to visualize your frequency response with respect to the time. So you are able to see scope. In the scope, you are able to see the frequency deviation with respect to the time. So we are getting delta f of s at its feed to the scope. Here you are able to see the delta f of s, how the delta f of s is varying. Now tell me, did I miss any other block for the load frequency control? First order approximation.
1 by R.
Perfect. We have the 1 by r. So for that, it's like a gain, some gain. So go to your MATLAB library browser and you can use the continuous blocks. You can see the gain block. So just drag and drop here. Just simply rotate R5. So click right click here. Sorry, right click here, and you can see rotate and flip. So just you can clockwise direction rotate it. So you can again rotate in clockwise direction. Yes. So what is the value? What is the value here? 1 divided by R value. 1 by R value. 1 divided by 3. Okay, 1 divided by 3. So what is the input for this 1 by R or 1 by 3? What is the input, from where you are getting the input for this block? From where we will get the input?
Delta F.
Perfect. Delta F. So delta F is here. So this the input is coming to this one, and the output is going to output is going to. So delta F is coming. It is a 1 by R, and now this is going to
Minus.
where? Minus sign here. Perfect. So this is the complete load frequency control diagram of a power plant with first order approximation. With the first order approximation. So what is your expectation? How the plot will be? Maybe the students who attended last yesterday's sixth hour and seventh hour, they are able to. So how your expectation, how your frequency variation should be in this plant? So this is the first order approximation free governing operation plant. So how your frequency response variation will be?
Slowly increases and reaches a steady state value.
Yes, not slowly. The deviation will be slowly increases in the negative side. It's the negative side and the positive side. Demand is here, load demand is positive 0.01. That means demand is increases. If the demand is increases, delta F value is negative or positive? Delta F, change in frequency, negative or positive? When the load is increases, it will be
Negative, sir.
negative. It will be negative. So in the negative side, your deviation will be increased and later it goes to the steady state. Okay. So just I want to run this simulation for the 7 seconds. I want to run the simulation for the 7 seconds, just to stop time 7. That means the simulation will be running from the 0 to 7 seconds. Stop time equal to 7. So now click on the run button. Compiling 100% completed. Now click on this code block. Click on this code block C. And I will increase the time. You are unable to visualize perfectly. Now I want to increase the time for 10 seconds. That means your simulation will be up to 10 seconds. So again run it. See, I think you agree. What is your interpretation from the simulation. What is your interpretation from the simulation? See, what is this? This axis represents. What is this axis represents? This one. What is this minus 0.005, 0.01, all represents? What is this? What is the value? These values represents what? Tell me what you are feeling. Please tell me what is these values. It is 0 here, and it is minus 0.005, 0.01, all are minus values. What is what all these values represent?
Delta F.
Perfect. It is the delta F. It is the how frequency deviation is this. Your frequency will be deviated. It is the frequency. Delta F value will be increasing in the negative side. That means your frequency decreases, and it goes to the steady state value. What is the steady state value? Santosh, yesterday we derived for first order approximation. What is the steady state value? I think we calculated yesterday with the KPS equal to 100, TPS equal to 20, all those things. I think you are Santosh, right? You gave the answer for me yesterday.
Yes, sir. Yes, sir. I'm saying.
Minus 0.029.
Perfect, perfect. See, this is the 0.03. Somewhere here it is the 0.029. So it is saturated at 0.029. Understand? So this is how frequency deviation will be. So your frequency will be decreases. That means frequency deviation increases. That means your frequency will be away from your nominal value. Your frequency deviation increases and goes to the at steady state. So it is a steady state frequency deviation. This is called steady state frequency deviation. From here to here, it is a steady state frequency deviation, and it is a dynamic response. How your frequency deviation is varying with respect to the time. Now my question is, why there is no frequency deviation in this period? Is why frequency deviation equal to 0 here? Why frequency deviation equal to 0? From here to here, from 0 seconds to 5 seconds, in this portion from 0 seconds to 5 seconds, frequency deviation equal to 0. Why?
No load.
Not no load. No, that's not case. It's not no
Function
load.
after 5 seconds, no, sir.
Your on the power plant, there is a change in load at the time of 5 seconds, not before. So before there is no change in load. There is no change in load before that one. So there is no change in frequency. Frequency deviation equal to 0. But load is changes after 5 seconds. So when the load is increases after 5 seconds, your frequency will be deviated. This will be deviated, and finally it goes to at a steady state condition. So this is the frequency deviation. The frequency deviation value equal to minus 0.029. Hope you understand, right? So your frequency deviation equal to 0.029. That means so we are getting frequency deviation, steady state frequency deviation equal to minus 0.029. Now tell me what is the system frequency? If you assume initial frequency f naught equal to 50 Hz, now what is your system frequency under steady state condition because of the 0.01 change in load demand positive? What is the system frequency now? Let us assume initially if there is no change in load, the system is operating at the 50 Hz. Now if the load is increased by 0.01 per unit, now what is the system frequency under the steady state condition? F equal to. So please open up. Whether it is even if it is wrong, no issue. I will correct it. Right? What system frequency?
F naught minus delta F, sir.
Perfect. Your system frequency, new system frequency F naught equal to F naught plus delta F. So that is equal to F naught equal to 50 and delta F equal to minus 0.029. So that's equal to 49.971. So this is your new system frequency under the steady state condition. That good. Hope you understand. This is a sub case. This is a case 1, first order free governing operation. Why it is a first order free governing operation? Because it is delta t is equal to 0. It is a free governing operation. And the first order approximation by choosing the KRG into KT equal to 1, TRG equal to 0, TPS equal to 0. That's why it's called as a first order approximation. Okay. With the first sub case, that is the load is increased by 0.01 per unit. 0.01 per unit. So load is increases, so your frequency decreases, so your delta will be in the negative side. Now my question is, I want to simulate for the second case. What is the second sub case? What is the second subcase? In the case 1, what is the second subcase? First subcase is the delta PD equal to 0.01 per unit. That means the load of the power plant will be increased by 0.01 per unit. That we simulated. Now what is the second subcase? Anyone? What is the second subcase? So actually we discussed it right earlier in the first previously. So two subcases. I think yeah here. So case 1 we are testing first order approximation with free governing operation. First order approximation with free governing operation. So again in this case we have the two subcases. One is the delta PD positive, that is we are considered delta PD equal to 0.01 per unit. What is the second subcase?
minus 0.01.
Perfect. Now we take the delta PD is negative. That means delta PD equal to minus 0.01 per unit. That means your change in load is a negative. That means your load is decreased by 0.01 per unit. If the load is decreased by 0.01 per unit, how the frequency deviation will be? Now we are going to observe. Okay, that is second step. So you can use the same. You can use the sorry. You can use the same diagram. Yeah. Okay. Now this is the already we simulated. It's completed. We already simulated. So this is the for the positive load change. Now I want to simulate how my system frequency will be. How frequency will be. How the frequency deviation will be changes with respect to the time. If the load is decreased by 0.01 per unit. The load is decreased by 0.01 per unit. Now please tell me where I have to change. Now I want to I am assuming that I have a power plant. In the power plant, the load on the power plant is decreased by 0.01 per unit after 3 seconds. So I have a power plant. I am running the power plant under the normal operating condition. But after 3 seconds, the load on the plant is decreased by 0.01 per unit. If that is the case, what changes you have to make in this complete model? So the scenario is after 3 seconds my load is decreased by 0.01 per unit. Now I want to observe the frequency deviation, how the frequency deviation will be with respect to the time in this scenario. So what changes I have to do in the simulation here? Anyone? What changes I can make here? Please open up. So I think you are clear, right? Are you able to hear me? Can you please respond? Are you able to hear me? Yeah.
Repeat again, sir.
Yes, I will repeat again. So this is the first case is first sub case is completed with the positive delta PD. That means the demand and the power plant is increased by 0.01 per unit after 5 seconds. Now I want to simulate another case. Now my power plant is running under normal condition, but after 3 seconds, after 3 seconds, my demand is decreased by 0.01 per unit. Now I want to observe the frequency deviation with respect to the time. So in that simulation, where I have to change, where I have to do the modifications. Because
Step function, sir.
exactly. Why I am saying all those things means in the examinations, we will not provide the same case for all. We will provide the different cases for the different people. So you have to know where the changes you have to incorporate in your simulation model. Now, Santosh, please tell me where to change do the changes here.
Step function.
Perfect. In the step function. Now in the step function, what I have to change? Please tell me.
Time 3 seconds, sir.
Perfect. So because after time 3 seconds, the load is decreased by 0.01 per unit. Now, only that, anything else?
Final value.
What's the final value?
Minus.
Minus.
Minus
Perfect.
0.
Perfect. Minus because it is a decreasing. By 0.01 per unit is decreased. That's it. Apply. Now we are going to simulate it. So if you simulate, what will be the difference for the first case and the second case? What is the difference for
We
the
will get
first?
graph
Ah,
upside, sir.
yes, yes. So your frequency deviation is a positive. So initially your frequency will be deviation will be increasing with respect to the time in the positive side and goes to the steady state value. Right? Now I'm going to simulate it. Now open the scope block. See. Are you okay, right? You are able to understand, I think so, right? So why this is a 0 up to 3? So you are going to plot all the things. Okay. Chapana Vidyanti? Why is the 0 here?
Time,
What? Santosh?
time, sir. We have given that 3
Yes.
seconds.
On the power plant, loading changes at the time of 3 seconds. Previously, there is no change in load. If there is no change in load, your frequency deviation is 0. But when the load is decreased by 0.01 per unit, then the frequency increases. The frequency deviation will be increases and goes to the steady state value, and the steady state value is 0.029 plus. Okay? So this is the steady state. Now tell me, what is the system frequency in this scenario? What is the system frequency in this scenario? Initially, let us assume you are operating at the frequency f naught equal to 50 hertz. So when the load is decreased by 0.01 per unit, what is the steady state frequency? F value. What is the steady state frequency? F equal to f naught plus delta f. So that's equal to 50 plus the frequency deviation is 0.029. So that is the 50.029 hertz. That's it. Understand? Yes. Okay. So now these two models you are going to simulate as part of first order approximation. First order approximation, free governing operation, and you have to observe how the frequency deviation will be. Okay. Now I will save this one, and I will take the snapshot print screen, and I will share through WhatsApp, and you are going to simulate in the lab, and you have to prepare the notes. You have to prepare your observation accordingly. So first order approximation, what the KPS, what the TPS, what the KSG and the K2E, what the TSG, what the TT, all the values you have to incorporate in your observation and come to the lab with those values. And also I will attach okay, the screenshot only I will attach, you can see it. Okay, fine. You are clear now, I think somewhat. Okay. Now we move to the case 2. What is the case 2? Now I want to move to the case 2. What is the case 2 now?
Free governing operation.
Only free governing operation. There is no first order approximation, only free governing operation. So I want to open the new block and I want to save this project on the desktop load frequency control with the name free governing operation only FG. Okay, FG. Now tell me, now I'm trying to explain free governing operation. Later we will go to simulation. Now rather your power system block. So it is the delta PC of S, and here you have plus and minus. So here you have KSG divided by 1 plus STSG speed governor, and here you have KT divided by 1 plus STT, and STT, and here you have again difference block plus and minus, and the step change load delta PD, and we have the power system plant KPS divided by 1 plus STPS, and this is the delta F of S, and this delta F of S is coming feedback through the speed regulation percent 1 by R. That's it. Done. So this is the generally your single area load frequency control diagram or isolated power system. So if it's a free governing operation, what changes you have to do? Now it's not a first order approximation. It's not a first order approximation. Okay. So it is a only free governing operation. First case one is a first order approximation along with the free governing operation. Now it is only free governing operation. Now, if it's a free governing operation, what assumptions you are free governing operation means what I have to do here? What will be free governing operation?
Delta PC is equal to
Yes, it
0.
is a delta P is equal to 0. That means just simply you have to keep a constant block with value 0. Okay. And what about the remaining all values? I will write here. Then what happened? You have to keep KSG into KT equal to 1. That means you have to adjust the length of the linkage mechanism such that KSG into KT equal to 1 and keep TESG equal to 0.4 seconds and TT equal to 0.5 seconds and KPS equal to 1 by B, where B equal to generally 0.01, that's equal to 100. So KPS equal to 100 and TPS equal to 20 seconds and R equal to 3. So based on all these values, we need to simulate the complete block. That is, I have a power plant where KRG into KT equal to 1, KPS equal to 1000, PSG equal to 0.4, turbine time time 0.5, power system time 20, speed regulation coefficient R equal to 3. Done. So these are parameters. These are the configuration parameters of a power plant where I want to simulate the frequency deviation with respect to the change in demand. So now based on these parameters, you are going to simulate. You are going to simulate. Please note it down everything. Please note down all the parameters. Okay. So in the examination, I will change these parameter values. So accordingly, you have to simulate it. Okay. Now tell me, these two are the cascaded block, right? These two are the cascaded blocks. Okay. So how we can represent this complete block diagram? These two are cascaded blocks. So I can represent these two blocks with a single block. What is the value, Amma? If you represent two blocks as a single block, what is the value? If these two blocks I want to if these two blocks I want to keep it as a single block, what I have to do here? What is the resultant block? Anyone please?
KSG into KT by S square TSG.
Yes. KSG into KT divided by S square into TSG into TT. Ante kadamma? Plus
Yes, sir.
S into TSG plus TT plus 1, right? Ante kadamma?
Yes, sir.
Yeah. So from here you can represent this block diagram. Instead of these two, you can represent single block diagram. So what is the KRG into KT? What is the KRG to KT? 1
1.
divided by. So S square into TSG to TT entama? TSG equal to 0.4. TT equal to 0.5. What the TSG into TT? 0.4 into 0.5 kadama? 0.4 into 0.5. What is the value? 0.2. Right? So 0.2 into S square. S square coefficient is 0.2 plus what about S coefficient? TSG plus TT. So TSG plus TT. What is the value? TSG plus TT?
0.9.
0.9. So 0.9 into S plus what about next one? That's it. So this is the block. This is a combined block for both speed governor and also turbine. And what about this one? ఇదేమవుతుందమ్మా KPS by 1 plus STPS. KPS value 100, KPS value 100 and TPS value 20. TPS value 20. What about the R value? It is a 3. Right? So now we have to construct the complete diagram again in the MATLAB and we need to observe. Okay? Is it clear, Amma? Is it clear? So, can you please respond?
Yes, sir.
Yeah. So I will share the same screenshot here again. So you have to do all the things. So this is helps you for case 2, only free governing operation. And one more change. So I am assuming that there is a change in load demand on the plant at after 5 seconds with the value 0.01 per unit. Okay, that means I have a power plant. It is running smoothly without any load deviation. But after 5 seconds, my demand change in demand equal to 0.01 per unit. That's a positive. Positive means my demand at the plant is increased by 0.01 per unit. Okay. Now helps me to simulate this complete block diagram. Helps me to simulate this complete block diagram. Go to MATLAB. Yeah. So first tell me which block I have to take.
Constant block.
Perfect. So click on the library, take the constant block. So what is the value of the constant block?
0.
0, because it's a free governing operation, delta is equal to 0. Next,
Adder block.
you can take a adder block. So you can go to math operations and adder block, but you have to make it a subtraction block because one is a plus and another is a minus. Plus and minus. Okay, good. Now this delta PC is connected to the plus, right? What next?
Transfer function.
Transfer function. So go to continuous block and you can see the continuous section and you can see the transfer function. Now tell me what I have to do in the numerator.
1.
1. So no need to change 1. What about the denominator? Denominator you
0
have
0.02.
yes 0.2 I think so. 0.2 or 0.02. What is the value? Is it 0.2 or 0.02? You can see I already shared, right? Screenshot already shared with you. So what are the values? 0.2 into s square, 0.9 into s and 1, right? 0.2 into s square, 0.9 into s and 1. Based on the KSG KT equal to 1, TSG equal to 0.4, TT equal to 0.5. So based on these values, so the transfer function will be 0.2 CST s square plus 0.9 into s plus 1, right? So now tell me, numerator okay, what of denominator here, what I have to write?
0.2, 0.9 and 1.
Yes, 0.2, 0.9 and 1. That's it. So you can enlarge it, otherwise you are unable to see. Is it right? Okay. I think you are getting the same transfer function. Just connect these two. What next?
Adder block.
Exactly. You have to keep the adder block. So go to common using blocks or math operations and go to adder block. Done. So in the adder block, you have to on the first side you have to keep the negative because that is connected to the minus and plus, and this transform directly connected to the positive terminal. What about this negative? Where to connect this negative?
Delta PD.
Delta PD. So how we represent delta PD in the simulation? How we represent
Step function, sir.
step function? Perfect. Step function. Go to sources and click on the step function. Drag and drop here and connect this one. Now double click on the step function. So tell me what I have to do. Where the change I have to incorporate? What the change I have to incorporate? Based on the problem set which I have given to you.
Final value 0.01.
Yes, final value 0.01. Good. 0.01. Next. That's it. Or anything else?
Time
Exactly. What are the time? Step time?
5 seconds.
Perfect. 5 seconds. That's it. Apply. Okay, done. Now, what next? Which block we have to connect next?
Transfer function.
Perfect. Transfer function. So connect the transfer function. Where is the transfer function? Yeah, transfer function. So tell me what is the numerator?
100.
100. And denominator values?
21.
20 and 1. That's it. So connect these two. And what is the outcome of this KPS block, that means power system block? What we are getting here? What is the outcome? What is
Scope,
the
sir.
delta F, right? And you want to visualize the delta F, dynamic response, how delta F is varying with respect to the time. So for that you have to connect the scope. Go click on the things, select the scope and drag and drop here. So scope is used to observe the output, to see the dynamic response of your frequency deviation. Now tell me what else I have to add?
Gain block.
Gain block. That's 1 by R. So you have to add the gain block. Gain block. This is the gain block. Okay. Just rotate this gain block. Yes. And what the value of the gain? Gain block value entama? What the gain block value?
1 by 3.
1 by 3. Good. Now from where you will get this output for this gain block? Input ఎక్కడ వస్తుందమ్మా gain block కి?
Scope.
That is from the delta F. And this is output going to
Negative.
Negative.
That's it. That's it. That's how we build load frequency, single area load frequency control diagram under the free governing operation. In the free governing operation, not first order approximation. Now tell me, what based on yesterday's discussion, how your output looks like?
Fluctuation.
Initially it is a fluctuating, later it goes to the steady state value, right? Antenamma? So during the initially
Yes.
it is a oscillating and finally goes to the steady state value, certain frequency deviation. Agree? Okay. So now I am trying to simulate this diagram for the 10 seconds. And see here the output. See, it is the fluctuating, but you are unable to see the whether it is going to the steady state or not. What I can do? నాకు కనిపించట్లేదు కదమ్మా అది స్టడీ స్టేట్కి వెళ్తుందో లేదో తర్వాత అనేది. సో నేను ఏం చేయగలను? వాట్ ఐ హ్యావ్ టు డూ? ఏం చేయాలి?
Increase times.
Perfect. We have to increase the time. So just I want to keep 20. I want to run the simulation for the 20 seconds. That's it. See? Otherwise you can increase the further 25 or 30. 30 seconds simulation. See, so initially it is a oscillating and it goes to the steady state value, and this is your frequency deviation, steady state frequency deviation. Agree? Now tell me why this is the constant up to here?
No change in load.
Yes, there is no change in load till 5 seconds. At 5 seconds where load demand on power plant is increases. So as the demand on the power plant is increased by 0.01, your frequency will be decreases. So it's a negative value. Delta F is a negative. The frequency decreases and it is oscillating and finally goes to the steady state value. So it is the frequency deviation. What is the frequency deviation here? It is around 0.029. So almost. So this is your steady state frequency response. If it is a first order approximation, it is continuously exponentially decaying. But in this case, it is a varying. And why it is a negative here? Because demand is increases. So frequency decreases. When the frequency decreases, that means your frequency deviation is a negative. The frequency deviation is negative. Right? I think it's clear with you. Okay, Nama? Okay? Oh, you are able to understand. Now, this is the case 2, free governing operation. Now, in the case 2, sub case 1, first case, where delta P is the positive equal to 0.01. Now, what is the sub case 2? And we need to simulate the sub case, second sub case. So, what changes? Second sub case is tells about what, and what changes you have to incorporate in this block diagram. That's a question from you. For you.
Minus 0.01.
Yeah, in the step changing load, what I have to do? You have to keep the minus 0.01. So we are, let us assume sub case 2 is I want to I have a power plant. Initially, the operating normally, but at 3 seconds, after 3 seconds, and the demand on the system is decreased by 0.01 per unit. Demand on the system is decreased by 0.01 per unit. See, if it is a problem statement, so what things you have to incorporate in the simulation diagram? One thing is you have to keep minus 0.01 as the final value, delta PD, step change in demand. Minus 0.01 means demand is or load is decreased by 0.01 per unit with negative, 0.01 per unit decreasing. That's the negative sign. Anything else? Anything else? Everyone. So I want to simulate my power system. Initially, it is under normal operating condition, but after 3 seconds, the load on the plant is decreased by 0.01 per unit. Now I want to observe the frequency deviation.
Time 3 seconds.
Yes, time 10 you have to keep as a 3 seconds. That's it. Simply apply and okay. Now, if I simulate this block diagram, so what are your expectations? How your output will be? Your frequency deviation will be? How frequency deviation with respect to the time?
Positive.
In the positive side, because the frequency decreases, your demand is decreases, when the load is decreases, your frequency should be increased. The frequency increase outunante, your frequency deviation is positive. So delta F will be in the positive side. So on the positive side, your frequency will be initially it is oscillating, later it goes to the steady state. Right? Now simply simulating. That's it. See? For initially for 3 seconds, there is no frequency deviation because there is no change in load. But after 3 seconds, the demand is decreased by 0.01 per unit. So frequency is increasing. Frequency deviation is positive, and later it goes to the steady state condition. You have to take all the pictures. And you have to take the printouts, and you have to write here. So free governing operation with decrease in the load by 0.01 per unit. So all the things you have to do. So hope you are able to later hit the steady state. Initially it is oscillating, and in this portion there is no frequency deviation because demand starts decreasing at 3 seconds time. Hope you understand these are 4 block diagrams. Now question is, if you observe free governing operation, or if you observe first order free governing operation, there is some frequency deviation. So frequency deviation 0 unte, that means your system is operating at the nominal condition, nominal frequency, that is 50 Hz frequency. But if there is a frequency deviation, that means your system is not operating in the nominal frequency, 50 Hz frequency. Actually, our motto is we need to operate the system at the nominal frequency. Slight variation is okay, but you have to maintain near to your normal frequency, that is 50 Hz. But the thought happened in the both cases, either in the first order approximation or in the free governing operation. Why?
We are not changing the speed changer.
Right. Because here in all the cases, we are assuming that delta PC equal to 0. That means we are not changing the delta PC. That means change in position of the speed changer. Speed changer is fixed. When the speed changer is not changing, fixed, then your valve also will not open or not close. It's also fixed. So that's why you are maintaining the deviation. You are getting the deviation. Your frequency is not come to the normal value. ఎందుకంటే so load increase అవుతున్నప్పుడు frequency అనేది decrease అవుతుంది. Accordingly, you have to open your steam valve. Then only again frequency going up and reaches to the nominal value. But we are not controlling the steam valve position. We are not changing the speed changer position. We are keeping speed changer as a fixed by keeping the delta P equal to 0. So because of reason, in both cases, you have some frequency deviation. So if you want to, but as an operator, your main goal is from this control system block, your main goal is you need to operate your system at the normal frequency 50 Hz. If you are able to maintain the frequency 50 Hz, what is the delta F? Under steady state, even though suddenly load is increases, frequency coming down, then you have to open the steam valve by giving the signal by changing the speed changer position. Steam valve will be opened, more amount of steam will be goes, then the generator speed will be go up, and frequency increases and reaches to the nominal value. So if you have to control the speed changer position in such a way that even the load varies, after certain period of time, your system again regain its nominal position at the normal frequency or nominal frequency. So that is the case 3. For that we are using the PI controller. We are using the PI controller. What the PI controller will do? The PI controller will sense the frequency deviation and feed the signal to your speed changer, and speed changer will be changes accordingly based on your frequency deviation, and it open the steam valve or close the steam valve, and finally your system will be regained to your normal frequency. You are agree? I think so. Okay, Nana? So I'm going to discuss the last case. So it is a PI controller, case 3, PI controller, PI controller. Okay. So again, tell me. So draw the block diagram. Plus and minus. Again, I want to use uh, the same parameters I want to use. One is KSG into KT equal to 1. So TSG equal to zero point 0.4 and TT equal to 0.5. Okay. If that is the case, what is the equivalent block diagram for the both steam turbine and governing block diagram? What is the equivalent block diagram for both? ఏమొస్తుంది మీకు చెప్పగలరు ఎవరైనా? Based on these 3 values, what we are getting here? Please respond. We have 30 more minutes.
1 by
Yes, because KG KT equal to 1 divided by please
1 plus 0.4 SP, sir.
0.2 into s square plus 0.9 into s plus 1, and here what we have plus and minus, and here the delta PD of x, that is the change in load demand. And again coming to the power system block, we are assuming that KPS equal to 1 by B, where generally B value equal to 0.01 per unit, 0.01 per unit. So KPS equal to 100 and assume TPS equal to 20 seconds. Now tell me what is the block diagram here? What's the block diagram? Mark, please respond fast. Hmm?
100 by
100 divided by
1 plus
20s plus 1 or 1 plus 20s. Okay. Now this is your delta F of S. Now one feedback is coming through 1 by R, and we are assuming that R equal to 3. So it is a 1 by 3. It is goes to the negative. And tell me, so this is the plus, right? And what about the delta PC? It is a, so here is the PI controller. It's not a free governing operation. If it is a free governing operation, delta PC equal to 0. That means your speed changing position is fixed. You are not opening the valve or closing the valve, right? But now it is a case 3. You are controlling your speed changer accordingly based on your frequency deviation. Use the PI controller. So what I am doing is, so your PI controller, let's assume this is the PI controller. So PI controller, let's come to the your PI controller. PI controller means it is a some KI divided by S. KI divided by S. So it is the KI and it is multiplied with 1 by S. Then KI by S. Okay. And it sends the frequency deviation and send the signal to your speed changer, and speed changer will be adjusted. either increasing or decreasing. So this adjustment will be done until your frequency deviation equal to 0. If the frequency deviation equal to 0, no input going to the your speed changer, your speed changer will not change. Your speed changer position will be changed until you have the delta PC. So delta PC value if there is a frequency deviation. And here we are considering the Ki value equal to 0.09. 0.0. Okay. Now this is the PA controller, but there is no time today. In tomorrow's class, I am going to explain why. So what is the? Please tell me, friends, if I use a proportional integral controller to feed a signal to the speed changer based on the input coming from the frequency deviation, what is your expectation in the steady state frequency response of the power plant? Anyone? I will repeat once again. If I use a PA controller which sends the frequency deviation and send the signal to the speed changer, accordingly your speed changer position will be updated. Okay. So based on your frequency deviation, based on the updation in the speed changer position, your valve will be opened or closed. So this will be done until your frequency deviation equal to 0. Okay. Now my question is, what is the steady state frequency deviation if you use the proper PA controller in the low frequency control system?
Zero.
Perfect. It's the 0. Because until it come to 0, until delta f equal to 0, your speed changer will be continuously monitoring, continuously updating, continuously varying. So steady state value equal to 0. So in case of the PA control, that's what we want actually. If the delta f equal to 0, what is the system frequency? Under steady state condition, what is the system frequency even though load changes? If you use the controller, PA controller for this purpose, so what will be the system frequency even though load is increasing or decreasing?
0.
0. No, 0. No. Frequency deviation is 0. I am asking system frequency.
50.
50 only. Nominal frequency only, right? Done. Now again we are going to simulate the same scenario in the two cases. One is the positive PD, that is the 0.01. That means load is increasing, and negative PD, delta PD. Sorry, delta PD. Negative delta PD, that is the minus 0.01. In both cases we are going to simulate. Okay. So total 6 diagrams you are going to simulate, and you have to show the 6 outputs. So we don't know in the examination you are going to simulate all 6, or I will give a specific problem for this specific student, not all to single person. Okay. Now we start working on new project. Yeah. So I want to save it as desktop LFC. It is a PI control load frequency control. Okay. Don't keep any icons. So tell me. So which block first I have here? So we will take the. Can we take a constant block with 0 now? Can we require? Can this constant block with 0 is required? A constant block. Initially we started with a constant block with 0 value in the for the two cases. Now the third case you require a constant block with 0 value.
No.
No, sir.
Not required because the delta p is not 0 now. So we have to keep it aside. Now I want to take the adder block. The math operations. Take the adder block. In the adder block, we have the plus and minus. Yeah. Plus and minus. Done. And now tell me what I have to keep here.
Transfer function.
Perfect transfer function. So continuous and take the transfer function. Now what is the transfer function value? Numerator.
1.
This is the transfer function which is a resultant block diagram of the cascade connection of the speed governor and turbine. So numerator is there 1 because Kg into Kt equal to 1 we are assuming. So what about the denominator?
0.9.
0.2 I think. 0.2 SS
Yes, sir. 0.2,
Ah.
0.9, 1.
0.2, 0.9 and 1. That's it. Done. Okay. So just connect it. Now tell me what I have to add and further.
Adder block.
Yes, great. So just simply use the adder block, and you have to keep one minus and plus here, and connect these two. So where to go? This minus n.
Step function.
Step function. So go to sources and use the step function. So assume there is a step changing load by 0.01 per unit after 5 seconds. So what I have to do?
Time 5.
5,
Final value 0.01.
0.01. So there is a increasing the load by 0.01 per unit. What next?
Transfer function.
Perfect. So use the transfer function. Just simply connect the transfer function. So what the transfer function here? Value is numerator
100.
100, denominator
21.
20s plus 1. Perfect. Next. So from the power system block, you will have the frequency deviation. What I have to connect here?
Scope.
Scope. Just simply connect the scope. Connect the scope. Done. Okay. What next? So
Gain.
what is
Sir.
gain block? Perfect. You have to use the gain block. So just connect the gain block. This is the 1 by R, right? So where you will get the input from here? This one.
Scope. Scope, sir.
Oh, from the delta. This one goes to output of the gain block.
Adder block.
Adder block negative side. What is the value of the gain?
1/3.
1 by 3 because R equal to 1 3. What else? Now you have to include the PA controller, right? So for the PA controller, what I have to add? I will show this one. See, PA KI by S, KI by S. This one I have to include. Okay, this one I have to include. Okay, so this is the gain, and this is the 1 by S integral, proportional integral. So tell me,
Transfer function.
transfer function and gain block, right? So use the first gain block, use the first gain block. So what is the value of this gain block? Ki value. Ki value. Okay, Ki by S kadama. So Ki by S. So Ki value 0.09 and one transfer function. You can see here. See?
1 by S.
Yes, 1 by S. Okay. So 1 by S means we have to include a transfer function. Now we have to include a 1 by S, right? Transfer function. Continuous. Just so what is the value numerator?
1, sir.
1. Denominator?
1
0
0.
and 1.
1 0. First one is S power 0 and from the right to left, S power 0, S power 1, S power 2 like that. So S power, this is the 0, there is no constant. S coefficient is 1. S coefficient is 1, this is a constant. Apply 1 by. Okay. So tell me from where you will get the input to this gain block?
Scope.
And this one goes to?
Adder.
And this one goes to?
Adder.
This is the delta PC, goes to delta PC. So you are getting the command signal to the speed changer from the PI controller, which will send the frequency deviation, send the signal to the your, and so this is changes, right? Yeah. So what is your expectation? So this is your PI controlled load frequency control system. Now I have a power plant. Initially running with the normal frequency, there is no frequency deviation, there is no change in load. But after 5 seconds, there is a change in increasing the demand by 0.01 per unit. Now I want to verify how my frequency deviation will be. Okay, Naman? Simulate. So we are unable to see. So simply increase it because only 10 seconds I am running. I am unable to see the steady state 0. So what I have to do?
Increase time.
Increase time.
Increase the time. So I am keeping the 30 now. Okay, just run. See how it will be. See why it is a 0 up to 5 seconds.
Step time is 5
Yes,
seconds.
because there is no change in load up to 5 seconds, but at the 5 seconds the load is increased by 0.01 per unit. Then your frequency is deviating, frequency is decreasing, but parallelly you are giving the signal to your speed changer. Then your wall position will be open, and slowly your frequency oscillates, and again it reaches to steady state value, steady state frequency deviation equal to 0. So with the free controller, what it will do is, when the demand is increased by 0.01 per unit, initially your frequency will be coming drop, and that how much it is dropping will be feedback back to the speed changer through the PA controller. Then your speed changer will be slowly open up your valve position. Then more steam will be flowing, and again your generator will be speed up, speed up, speed up, and again you are maintaining the same normal frequency with the frequency deviation equal to 0. Understand? Am I doing?
Yes, sir.
Yeah.
Yes, sir.
Yeah. So this is the in the third case subsection 1. What is the subsection 2? So assume I have a power plant. The demand on the plant or load on the plant is decreased by 0.01 per unit after 3 seconds. At 3 seconds, the load on the system will be decreased by 0.01 seconds. Okay. Now you have to simulate it. So what changes I have to make?
Step function value change.
Here
3 seconds.
3 seconds. Here
Minus 0.0.
minus because decreasing. That's it. Now simulate it. What change you observed here? Previously it is decreasing, negative side. Now it is in the positive side. And whatever it may be, finally you are going to the steady state frequency response equal to 0. అర్థమవుతుందమ్మా?
Yes, sir.
Yeah. So this is what completely about the single area low frequency control system. Okay. So you are going to simulate all the 6 block diagrams based on the parameters I have given. So where in the examination, so I will change the parameters. I will give some clue to calculate the parameters and to set the your step load changes, timings and load and everything. So accordingly you have to simulate it and you have to show your outputs. But whereas in the lab, so you have to do the same parameters what I have given to you. So you have to simulate all the 6 diagrams and show all the 6 plots and take the printouts of both the diagrams and the plots and submit the record next time after completing the experiment. So if you want, you can do it in your laptop also at home. Otherwise, there is one lab allotted for you for this afternoon Friday batch and Monday batch for the coming Monday. So the next Monday, this Friday, you have to do this what's called single area load frequency control experiment. Okay, Naman? Hope you understand the complete scenario. But this is about the simulation. We are getting the steady state value equal to 0. You understand the complete aspect, but we don't have much time. That's why because some people have to come to the college for the afternoon lab. That's why I want to close the class now. But in the classroom, I will explain mathematically why your steady state value equal to 0. Physically, you understand. So your PA controller will read the frequency deviation, will give the signal to the speed changer. Your speed changer position will be updated. Your valve will be either open or closed. This will be continuous process until delta f equal to 0. That's the physical aspect, and also we are visualizing here in the simulation. And mathematically, I want to prove. I have to do the proof, and I will do it in the Monday, that is next class. Okay, Naman? So thank you for your active participation, and I will share all these diagrams with you. 1 minute. And first one is free governing operation, and this is the PA controller, and I think one more. So this is free governing operation. Yeah, this is the free governing operation, first order free governing operation. So total 1, 2, 3, 4, 5, 6 blocks you are going to simulate it. Try to understand what I am doing. I explained everything. Hope you are able to understand. If you have any doubt, you can ask me. Okay. So just I want to close it. Just wait a minute. Just I will take a attendance. Just please respond. I will take the attendance. for the 2 hours. So give readiness please.